My name is Jason Stearns. I am the technical sales representative for CGIS in British Columbia, and we're lucky to have join us today Mr. Richard Laukam from ValvTechnologies. Richard is joining us from Houston, Texas, and just a little bit about Richard himself. He's responsible for developing technical specifications across North America for high-performance severe service isolation valves. Richard joined ValvTechnologies back in 2007 with responsibilities for global projects, subsequently leading the design team, and now involved in developing forward-thinking visions for emerging technologies. Richard recently held positions at IMI in the field of fluid controls. He graduated from Loughborough University with a Master's of Engineering and Management. He also holds a diploma in Industrial Studies, a postgraduate certificate in Management, and is a member of the Institution of Engineering and Technology in London. And I can say I've worked with Richard a lot over my 6 years with CGIS, and he's a wealth of knowledge and a pleasure to listen to. Just quickly, we're going to talk about some housekeeping items. So everybody unfortunately has been muted in this webinar, and I know everyone's probably super excited to get your questions across to us. So if I can ask, if you do have questions, if you hover to the bottom of the WebEx screen that you have open, you'll see the second icon, and we've got it circled in red there. It's the Q&A box, and that box will open, and you can then pose your questions to myself, Richard, our other moderator, Sam, and other CGIS individuals that are on the call that can help answer that question. So please feel free to push your questions forward. We want this to be an interactive webinar, not just us sitting here talking about and presenting on the slides. So we'd love to hear your guys' questions and thoughts and ideas across all of those areas. As well, you guys will all be receiving an email from Sam regarding the recording of this webinar, so you will have a copy for yourselves and your teams to reference in the future. And if anybody would like a certificate of attendance for attending this webinar, please just respond to that email and Sam will send you a copy of the attendance and you can file that away in your records. So quickly as well, I just want to talk a little bit about CGIS, who we are, and our relationship with ValvTechnologies. If you want to, so some of you may have worked with us in the past with other webinars and so forth. But just quickly with the background of CGIS, we're a valve automation company, and we really look at solving valve problems, and we do that by approaching the application. So we take an application-based approach and look at what the process conditions for that application are, what the valve's job is. Is it isolating or is it controlling? And how well does it need to do that job? And through partnering with companies and manufacturers like ValvTechnologies, who we've been working with 25 plus years, we're able to come up with solutions that are able to solve the problem the first time and give you the performance, service life, and cost of ownership that you expect out of your valves. And we are happy to do that all day, every day. Quickly, I will pass the microphone off to Mr. Richard Laukam, and we look forward to hearing your guys' questions and feedback throughout the presentation. Please take it away, Richard.
Thank you, Jason. Really appreciate the introduction there. And a hello and a warm welcome to everybody who's on this webinar. So the whole series is about hydrogen as a fuel for the future. And the way that we're going to do this webinar is we're going to talk a little bit about the general principles surrounding hydrogen, and then we'll look at valve design in the second half of the webinar. But the first place to start is actually our own sun. And our sun is mostly hydrogen, about 90% and certainly over. And there's two reactions that occur, and we have nuclear fusion and nuclear fission. And the sun actually operates by fusion. So we're basically turning, we're taking hydrogen, they're turned into helium. So we're fusing the two aspects of hydrogen. and then we actually get energy as a consequence out of that. Hydrogen makes up roughly 90% of all the elements or the atoms in the universe. So at first you might think it is relatively abundant. In reality, in Earth, it's actually pretty rare to find. So the only way that we can produce hydrogen is we have to find it from another substance. So just like electricity, we see it as an energy carrier, and we'll go through some of the hydrogen production methods to actually get us there. When we look at all the topics around decarbonization and we think about, why hydrogen when there are other ways in which this could be accomplished. If we take the United States, for example, around 5% of the landmass would be covered with solar panels or wind turbines to generate all of the electricity that is consumed in the United States. So that 5% of landmass is infeasible to do. It would be a huge amount of cost, and lots of infrastructural developments would have to take place. So although wind and solar will continue to be growing areas of renewable energy, we have to look at other methods as well. And so hydrogen, as I said earlier, is relatively abundant in the universe, but on Earth it's relatively rare. So what we do is we produce it from a feedstock, and that feedstock is either a hydrocarbon, so hydrogen and carbon, or it could be just water itself. If we do generate hydrogen from hydrocarbons, the downside of that is it creates carbon dioxide. And of course, with all the decarbonization efforts, it doesn't seem to make sense to have a clean fuel, but in a reforming process, we have this byproduct of carbon dioxide. And so one of the key ways that hydrogen is produced is through electrolysis, and we'll go through some of the techniques there. But one of the downsides of all of this is it often takes more energy to produce hydrogen than you can actually extract out of it or provide out of it when it's converted back into energy. So there still are challenges, whichever way that we look when it comes to decarbonization. But one thing is for certain, and that is hydrogen consumption is on the increase. So we have a graph here which shows hydrogen across the different years. And as you can see, the trend there is sharply going up. Hydrogen could either be used in refineries or in production of ammonia. But as the green cells show, it's still in the infancy stage when it's used as a fuel. But if we project all of these together for 2030, so in just about 6 years from now, then the amount of hydrogen consumption is going to more than double. So currently we're about 80 million metric tons per year, but we can see that rising to about 180 by the year 2030. So currently very little of it is for fuel, but the future potential for it being used as a fuel is still quite there. So 95% of all the current hydrogen production is from reforming. And as I mentioned, that is a large source of carbon dioxide. That's where we take a natural gas and we add steam to it. So the three production methods, we'll take something like a methane gas, would add steam to it, so water at high temperatures. It produces carbon dioxide and hydrogen, and of course there's the carbon dioxide byproduct. The other way to produce hydrogen is through partial oxidation. So we take a fuel, again, such as methane, we add oxygen, and the byproducts of that will be carbon monoxide, which of course is dangerous, and also hydrogen. But electrolysis is seen as one of the key areas of growth, and that's where we add electricity to water, and the byproducts there would be hydrogen gas and also oxygen gas. So when we say electrolysis, think of it as a big tank. There's a separator in the middle. On one side, we have a cathode, and on the other side, we have an anode. And across the cathode and the anode rods, we apply electricity. And once we do that, on one side of it, we will get hydrogen bubbles, and they escape through the top. And on the other side, we get oxygen bubbles, and they also escape in the gaseous form. So really, electrolysis is all about adding electricity to water, and we can produce hydrogen from that. You may have heard that there's different types of hydrogen, and if we go through the spectrum, if anything is referred to as blue or gray, it does mean that we're using natural gas, such as methane, to do steam reforming. The differences there is that there could be with carbon capture or without. If we look at black hydrogen, that means it was produced from coal. So again, the carbon intensity there is quite high, and typically there's no carbon capture. And the same thing also applies to lignite coal, which is referred to as brown hydrogen. If we're looking at renewable powers, that would be green. Nuclear, it would be pink. And solar, unsurprisingly, is yellow hydrogen. If there's pyrolysis involved, that'd be turquoise. And if it's just naturally occurring hydrogen, as you'd find underground, then that's just known as white hydrogen. So the different colors really refer to the production methods as to how we obtain that hydrogen, and also the intensity of the carbon as well. So if we look at the general properties of hydrogen, and perhaps the first thing that stands out is it's highly flammable. So whenever we have a reaction, it is exothermic, so that means it's the release of heat. The heat of combustion rate is about 320 BTUs per cubic feet, and so that is relatively high. It auto-ignites at around 500 Celsius, and if we look at the lower explosive limit to the upper explosive limit in air, it can be between 4 and 74%. Whenever it does ignite, the flame propagation speed is around 15 inches per second. So really what we're saying here is that hydrogen can be dangerous to operate. And so factors such as leakage are critical. We've got to make sure that there's no chance of that hydrogen escaping to the atmosphere, but more importantly, that it doesn't ignite and create a flame, which could be dangerous to people. So if we look at the hydrogen universe and we say, okay, the world is going to increase its consumption of hydrogen. It's going to be helping our decarbonization efforts. There's very specific ways to produce it, to make it viable. I guess the question now is when it comes to valve design, can we just take an out-of-the-box design and just put hydrogen through it? And actually, the answer to that question is no, it's not even possible. Because what would happen then is that we'll see hydrogen escape. So even if we took a zero leakage rated valve that has very stringent factory acceptance criteria, above the ANSI standards, perhaps even the ISO standards, even if it didn't leak and it was rated as zero leakage with the standard test procedures, which typically involve air, which is mostly 78% nitrogen, or if the tests were done hydrostatically with water, then zero leakage can be achieved. However, if you test that same valve with either hydrogen or helium, so the reason why we would test with helium is if we look at the periodic table, hydrogen is number one, it's the first element, the smallest element, and then helium is number two, but then helium falls within the vertical column of the periodic table of inert gases. So helium has similar properties to hydrogen when it comes to testing a valve, and so it's safer to test any equipment with helium than it is with hydrogen, and yet the elements are about a quarter the size of water molecules. So how does it impact valve design? Well, of course, avoiding escape is perhaps the biggest challenge. So something has got to change even in a relatively good design. For water or for air, it's just not good enough for hydrogen. And the other thing too is hydrogen, for it to be an effective energy carrier, a fuel for the future, the way that it will tend to work is a lot of these systems will be ultra high pressure systems. So we've got to deal with high pressure, avoiding escape. We've got to think about the dangers of testing all the equipment. But equally, there's very few industry standards when it comes to hydrogen. So much of it was built around oil, gas, steam, but really, all of these upcoming standards are not here today. We have one or two maybe, but it is going to be very much an evolving system. So when we look at what makes or what are the technologies that are required to have a valve deal with hydrogen, we've got a couple of things. The first is the coating technologies. So I focus on coating as a distinct difference to weld overlays. So weld overlays is where you have a high performance metal welded over a cheaper substrate, typically such as carbon steel. But a coating is not applied that way. A coating is much thinner. It's not a mechanical bond, it's actually a chemical bond. And so the way that coatings are applied, I mean, typically the term you may have heard, HVOF, so high velocity oxygen fuel. We accelerate particles supersonically. They hit a substrate at a very, very high force, and that creates a bond. The higher that force is applied, the stronger that bond is. And it was technology that was derived from the aerospace industry in the 60s and now has filtered its way down to valve design. But when it comes to coatings, which are really there as a hard-facing technique to prevent against wear and resist wear over time as valves cycle, porosity becomes a design consideration. And so whereas before, if a coating was perhaps 0.5% porous, which is one of the best on the market, I mean, typically most coatings are about 6%, have 6% porosity. Even 0.5% is not good enough because hydrogen can still escape through that. And so the technologies that has been developed really addresses any microcracking that could occur either in the base metals, the substrate, but also we have to remove porosity in the coatings itself. And the way that it's done is that hard ceramic particles are fired along with the coating to plug and fill any microcracking that could occur. That microcracking is critical for hydrogen surface, but it's not when you have water, air, or even gas. So the coating technology is something that has to be changed or advanced. The second thing too is when we look at the general designs of valves, they fall into a number of categories. There could be floating valves, seat-supported valves, or trunnion-supported valves, and each have their own advantages as well as disadvantages. But if you think about the general term floating valve when it comes to the geometry of the valve design, if the valve floats, so what we mean here is that the ball can float from left to right, assuming that the valve is in a horizontal position, then if the ball can float, then of course the valve is going to leak because that means that the ball is not in direct contact with the seat, and so escape can occur. Trunnion-supported valves are a little different. So they have two floating seats. So we have a fixed trunnion protrusion at the top of the ball, a fixed trunnion protrusion at the bottom of the ball, and then we have a series of bearings to hold that ball in place. So even though the ball is fixed axially, the seats do float in and out. So technically, if you have seats that float, then hydrogen can escape from that. And so one of the technologies that gets around this is an integral seat. So the seat itself is part of the end cap of the valve body. And so it's one contiguous component. By avoiding any welded in or pressed in seats and having that one contiguous component, it means there's no leak paths behind the seat. And that's one area where gases can escape. The other thing too with a seat-supported design is think of it as a solution where it acts like a trunnion, but it's actually not a trunnion. So what we're saying here is that the ball cannot float from left to right. And the reason for that is the ball is loaded against an integral seat under extremely high forces. So the higher you push that ball into the seat, the less that hydrogen escape can occur. And that's one of the design techniques that's used. The other thing that's got to be considered too is the materials of construction. So one of the disadvantages of soft-seated valves is that if they have any rubber components on there, and for whatever reason, if a rapid decompression was to occur, when hydrogen escapes rapidly or decompresses, rubber materials have got the risk of blistering. If they blister, then it only progressively gets worse. And so that's why a metal seated design, although metal seated designs are typically associated with higher temperatures, and most hydrogen applications are pretty much at ambient, not very high temperatures, but the metal seated design is really intended for the avoidance of rubber components on there if there was to be a decompression event that would occur. So that's seat-supported technologies. And along with that, the Belleville spring. So if we look here on this diagram in blue, the spring, which looks more like a washer rather than a coil spring, pushes that ball into that seat. And again, the intention there is to avoid any hydrogen escape or leak by, as you might more often refer to it, between the seat and the ball. So ultra high forces to push the ball into the seat. The design consequence of this, the downside, is you end up with a high torque valve. And it's just pure physics. So when it comes to hydrogen service, one of the downsides of this is we see valves with extremely long levers on there, or perhaps bigger actuators than you would have normally. But that is the side effect of operating equipment such as valves in such an application. So the spring technology becomes pretty important here. Materials of construction are also important. So whereas you have water, steam, or gas applications, those materials are generally suited to that application. It's a very sour application, highly corrosive. Then we make sure that there's the right high-performing alloys. But in actual fact, certain high-performing alloys may not be the right thing to use with hydrogen. So if we think about alloys such as Inconel, one of the engineers' favorite choices, it may not be applicable to hydrogen because we're concerned about embrittlement. If it's gaseous hydrogen, perhaps less so of a concern. But if it's what we call wet hydrogen, so it's in other words, it's mixed with other impurities, then embrittlement can occur. And what we mean by embrittlement is the metal actually fatiguing or detaching, as the photograph shows. So really what happens here is that hydrogen diffuses in that substrate. It forms bubbles at the grain boundaries, and that pressure exerts into granular cracking. And ultimately, the material loses its ductility and its tensile strength over time. So embrittlement is a concern, which is why certain materials, such as the Belleville spring, have to use different types of materials going forward.
Richard, we have a few questions that are coming in through the chat here, maybe I'll just start with the first one here. Um, do you use any vacuum sealing in addition to the spring seal?
We don't know. It's not a vacuum seal. It is just a mechanical spring that pushes the ball into the seat.
Thank you. The next question is, high temperature applications hydrogen service would like to know what packing material is usually used where fugitive emissions is kept to the minimum.
Yeah. So, I mean, typically companies like ValvTechnologies would use a graphite-based packing. But the problem with that is, again, you can have gaseous hydrogen escape from it. So it's not so much the material, but more the densities. So there are new types of packing that have been developed specific to hydrogen use. None of them are zero leakage, but we're looking at maybe 5 parts per million of FE emissions at that point. And that's the best available technology that we have today.
Thank you. And the last question, with the valve so tightly sprung against the valve, Will the valve ball seat surface also wear much quicker?
So that's where the coating comes into play, and the coatings are there to protect the valve components as they cycle. So even if you just took a valve and cycled it 100,000 times, that we've actually done in the laboratory, and then it's taken apart, it can be shown that there's very little wear even after 100,000 cycles. Now, of course, lab testing and field performance testing are two completely different things. So some of the accelerated live tests that have been performed have been done at high temperatures, extreme temperatures. Um, but yes, generally speaking, once we have the right coating, it's a hard-facing technology, and its intent there is to protect the substrate from wear. So it's the coating that does the job. And then it's the special type of coating that we apply that makes sure that it's not porous to hydrogen.
Thank you, Richard. Those are all the questions currently.
Awesome. So fugitive emissions, I guess one of the questions was leading this way. So all live loaded designs, that's always a recommended practice. So you have that constant the force there applied. Like I said, typically a graphite with a 316 stainless mesh is the way to go. Elastomers or plastics are not recommended. Um, but the stereotypical packing that you can get off the shelf may not be enough. As of today, there are no standards. We do have engineers who are working on what was known as the API 6Z task group force, and that is to address what emissions should be for hydrogen surface. So we probably won't see that stand until maybe 2025 at the very earliest. So there's really nothing available today to go to. But as I mentioned in one of the earlier questions, that there is packing that has been specifically developed for hydrogen service, but it's not truly zero leakage. It's about 5 parts per million worth of leakage. And that's actually at 10,000 psi of hydrogen, which is a fair reflection of how these systems are likely to operate under high pressure. There is one standard. It's the ISO 19880-3. It is a British standard. It talks about gaseous hydrogen, but really it is aimed towards fueling stations. It's one of the first, so it's a good document to go through. It's just over 60 pages. And the way that it's split up is it talks about the different types of valves. So whether it's a check valve, a gate valve, a globe valve, or a ball valve, there's certain aspects that's relevant there. But having read through the document, I would say in general, it's a good start because we're really talking about specifically high pressure applications. Some of the requirements that it lays down is the 102,000 cycles. So basically, 100,000 cycles under ambient, and then an additional 1,000 cycles at minus 40 Celsius, so a cold test, and then an additional 1,000 cycles at 85 Celsius, which to a metal seated valve is really nothing. 85 Celsius is really not that hot. But the intent here is that if a valve can pass these tests, then there should be no materials that result in any blistering. So again, it goes against rubber components that could be in there. The other thing that this standard, the ISO 19880-3, talks about is a bending moment test, which is somewhat unusual. So here we have to, or any manufacturer has to prove that if a moment was applied to the valve itself, that it can take that additional load. In reality, for most of the hydrogen systems that I've seen thus far, probably not too much of an issue. We tend to see a lot of tubing being used instead of piping. So from what we've seen, it tends to be the tubing that's more the limiting factor than the valve itself. But overall, the standard still has what it defines as an acceptable rate of leakage. And it's about 10 milliliters per hour at 100% of the cold working pressure. And I think that we won't see any true zero leakage standards coming out. And part of the reason for that is even if you just took a piece of pipe and shut it off on both ends and pressurized it with hydrogen up to 10 or even 15,000, over time, that hydrogen will seep through that piece of pipe. And so even though in valve design, there's more, I guess, chances for escape, whether it's leaked by between the seat and the ball, or whether it's through the fugitive emissions, even in a piece of pipe, there still is going to be some rate of leakage, probably not very much, and not to the extent where it's going to be dangerous. But that's why we foresee that there won't be any zero leakage standards, but there will be an acceptable range of standards that everyone will hopefully finally agree on. But this
Richard,
is
we have
what,
a question, sorry,
yep.
along materials of selection. So I'll read the question here. Can we use duplex stainless steel for high pressure hydrogen service applications?
Yeah, I would think so. I mean, I think any type of stainless steel should be fine. I haven't seen duplex just yet. I would say the most common material that has been chosen is pretty much 316, whether it's the cold temperature version or standard. But I mean, typically 316 is what we see.
Thank you.
So this is one way to test valves, and that is to have a hydrostatic shell test that's done at 150% of the cold working pressure, and the time is set to 3 minutes, which is greater than any of the standards. And the acceptance criteria there would be zero drops per minute. The other way to do it is to do a seat test. So you're testing the integrity of how well the seat works. I mean, this can be done again at 110% of the cold working pressure. The time in which it's done could be higher than all of the standards, and the test criteria could be zero. And a low pressure helium test can be done. And the reason why a low pressure test might initially seem counterintuitive, and that's because it's actually harder for a valve to pass a low pressure test as it would for that valve to pass a high pressure test. And the reason for that is the valve could be relying on the upstream pressure in order for it to seal. So by asking the manufacturer to do a low pressure test with helium, because it's safer than hydrogen, the molecules are almost as small, then it's much harder for any valve design to pass a 50 psi helium test than it is to do one that's at much a higher pressure. But again, if we compare this with the ISO equivalent, it was roughly half a milliliters for that same 3 minutes of duration. So the point here is that if the factory has a more stringent standards, the likelihood that hydrogen escape is going to happen actually decreases significantly. So the testing becomes quite important. So really, just to come to the conclusion, if we look at the advancements that we've seen in the design of valves, specifically for hydrogen, it really boils down to a couple of things. And one is the coating technology. So we talked about porosity and how to avoid that porosity. We talked about different geometries that there could be in a ball valve. So whether it's a floating design or a trunnion design, then really the seat supported design is perhaps the optimal out of the three geometries to assure that there's no leakage. We talked about the packing, which again, we can't just rely on standard packing. It's got to be designed specifically for hydrogen service. We talked about the general choice of materials, typically stainless steels. And also, we're really looking at even higher and higher stringency when it comes to factory acceptance testing, because as of today, the standards are really inadequate. And so the higher the factory acceptance testing, then the greater the chances that valve is the right valve for hydrogen applications. So really, that's the summary of the webinar. And I just wanted to end off by just giving a couple of photographs of some examples. This particular application is a dual application here, and you can see the ValvTechnologies valves with the red lever, and you can see how long the lever is in relation to the size of the valve. So again, that's the reason why it's long is simply because of the additional torque requirements. This application is a dual one, so primarily it's used as a truck fueling station. So this particular company has a fleet of long distance trucks that they wish to decarbonize with. And so hydrogen is being used as the primary fuel for these long distance trucks. But what this means is that for the operator to use these, there's not enough hydrogen stations built. The infrastructure really isn't there yet. So what this company did is they built an electrolyzer. So the electrolysis is the source in which they produce the hydrogen from water. Once the hydrogen is produced, again, in this system here that you see on the pictures, then some of the hydrogen is used for truck refueling, and some of the other hydrogen is used to be fed into a gas turbine. And so this is actually physically at a power station, actually in California. And so the hydrogen is blended with the natural gas, and of course, it's burned to produce steam and, of course, produce electricity by conventional means at that point. The reason why hydrogen, ultra pure hydrogen, is injected into the system is if you've ever seen a hydrogen flame and compare it to, let's say, a candle. So in a candle, you can see lots of smoke that comes out of the top. Well, if you ever burn hydrogen in that way, it's a very pure, clean flame. There's just no smoke. So if you think about it that way, what we're doing here is the turbine isn't 100% hydrogen, but by injecting hydrogen into it, we still have the energy that is required to produce electricity, but it means more and more of it is being, when it's burnt, we don't have carbon dioxide or carbon emissions as a side consequence of it. So the whole system becomes cleaner, and it helps everybody with decarbonization efforts. So that's one example. There's been other examples. So I talked about ammonia at the very start when we looked at the graph. So fertilizer production means that there's hydrogen systems there. We also see hydrogen compressor applications at refineries. And of course, the big one is this hydrogen as the way of the future when it comes to fueling up. And all these hydrogen systems are being developed. So that's pretty much the end of the webinar, and we'll open up the floor to additional questions. But really, just want to leave this in everybody's mind, and that is when it comes to the adoption of hydrogen and specifically the systems around it, whether it's valves or pipes or fittings, this is likely to be a marathon. It's not going to be a sprint. I think to get all vendors and manufacturers and EPCs aligned on the same page is going to take quite some effort. But it seems like we're heading this direction. It's not going to happen overnight, but it will take a number of years to refine the standards and to have us a bit more common across the board. But here at ValvTechnologies, it's worth just saying that we came up with the technology a little bit by accident. It wasn't really by design. And so about 12 years ago, we had a semiconductor company approach us, and they wanted valves that were zero leakage in helium. Well, back then we took the order and didn't understand the consequences of testing an out-of-the-box valve with just helium. And of course, valves that were ready to be zero leakage actually ended up leaking. And so it was an R&D project that we did to solve a specific problem. We didn't know about the future for hydrogen back then. 12 years ago, it was relatively benign. But it was because of that relationship that we had in semiconductor manufacturing that we developed the technologies and were able to guarantee that that ValvTechnologies could build, test, and assemble a valve that was truly zero leakage with hydrogen, ultra high pressure hydrogen. So it is interesting for us that we came into this by solving a problem and developed the technology 12 years ago, not realizing that we were very, very much ahead of the curve. And obviously now we're very happy to share some of that technology with everybody else. But that's the end of the main webinar, and we've got some time set aside for questions. So if anybody has any questions, if you just put them through Jason, then we'll do our best to answer them.
Richard, thank you very much. Well done, well presented. We do have a number of questions coming through, so I'll start at the top here. The first question is, for the socket weld end valves, does the seat need to be removed while being welded in? And if so or if not, why?
Yes, the answer to that question is no, it does not need to be removed. But when it comes to welding, there are some techniques that should be observed. If there's any post-weld heat treatment that is done, and that's really where the errors start to occur, then we always recommend that when the valve is insulated, that it's insulated to what we call the flat top. So if you look at the top works of the valve, there's a flat portion. The recommended guidelines are to never to exceed the insulation above that level. And the reason for that is once post-weld heat treatment is done, if the whole valve is insulated, there's no area for the excessive heat to escape. And then what happens is the internals could be overcooked. If the internals are overcooked, then the valve is going to fail pretty much from day one. So basically, the answer to that question is you don't need to remove the seat, but there are techniques that should be observed during welding.
Thank you, Richard. The next question is, does moisture in the hydrogen gas affect valve selection?
I don't think it affects valve selection. It depends how impure that hydrogen would be, because that could affect the materials of construction. So we talked about hydrogen embrittlement being a concern. So I don't, if it's just pure moisture, I mean, probably not. But if it's corrosive, then it could be quite a big deal. So in that case, we might have to look at other types of materials.
Thank you. So the next question, low pressure testing using helium, is it for both gaseous and wet hydrogen?
So the factory acceptance testing is really designed to be ultra pure helium. So it's not impure. It could be tested with hydrogen. Obviously, helium is just a bit more safer, but it would be tested with pure helium or pure hydrogen, not impure. And that's where the standards, in some ways, standards don't really help, because you're trying to compare different valve manufacturers to a set baseline, but that baseline may not be optimized to the application, if that makes any sense. So if we think about power generation, for example, where you have high pressure steam going through a valve, well, I don't think factories test to 500 Celsius. I mean, it's possible, but most factory acceptance testing is just done at ambient, and that's not really reflective of what the valve will see in service. And that's the other reason why we have pressure and temperature tables. So we compensate for that by over pressurizing during the hydrostatic tests. So if a shell test is done at 150% of the cold working pressure, what it means is that as the temperature rises, the maximum allowable pressure starts to decrease, and that's why you would over test a valve with a ultra high pressure to compensate for the temperature aspect of it. So yeah, I mean, standards are just baselines. They don't really reflect what goes on in the field.
Thank you, Richard. The next question, what is the maximum temperature your hydrogen valves are rated for continuous service?
Yeah, I would say it's pretty much limited to the temperature of the material itself. So if it's stainless steel, then typically 12-inch Fahrenheit, maybe 550 Celsius. Um, I mean, I have heard of high temperature applications. I would say in general, most of them tend to be at ambient, but the answer to the question is it's really limited by the abilities of the stainless steel.
Thank you, Richard. So a follow-up question to that one. What valve body and trim are currently available in market for gaseous hydrogen service?
The most common one is 316, so it could be 316L or just 316 standard. That would be for the body, the end cap, the ball, and typically the stem as well. The one thing that we have to consider with the stem design, though, is stainless steel is relatively soft compared to other materials. If we're talking about high pressures, then a stainless steel stem could twist. And of course, you can have a valve failure there. So one design solution to that is to double the diameter of the stem. So we can retain a 316 stem as well, but we'd have to overcompensate for it by increasing its diameter. So that would be a common trim for this application.
Thank you, Richard. Next question is bellows style packing something used in these types of valves for hydrogen?
Not that I've seen. I've not come across a bellows type. Um, Most of what we see would be like the wire mesh type for packing. But there are newer types that have been developed, such as vermiculite as a material that was designed specifically for hydrogen use.
Thanks, Richard. And then we've got one more here. Uh, on the moist on the moisture question on gaseous hydrogen, ValvTechnologies, when open, is like a piece of pipe and the seat is protected. Other types of valves, like wedge gates and globe valves, would have an exposed seat, and the velocities may have an effect on the sealing ability long term. Can you elaborate on what that means and the impact on using those types of technologies versus maybe the recommended features you've spoke about today?
Yeah, that's a fair question. So if we're looking at a different geometry of valve, and let's say we're looking at a wedge type of gate valve, then yes, the design of a wedge is such that the seat is typically welded into place. We have media that is, going through the bore of the valve, but it's also hitting the seats themselves. So welded seats are more cost effective to manufacture without any doubt. But the disadvantage is you have all this media, especially under high pressure, hitting that, and it could, let's say, erode over time. It certainly doesn't help. I would say that under very high temperature conditions, yes, that the seats are not protected, and so the valve can eventually leak. If it's ultra pure hydrogen, I mean that phenomenon can still occur, but less so when it's ultra pure high pressure hydrogen. So yeah, it helps in the design of any valve if the seats are protected. I mean, a ball valve is a good example that the seats are mostly protected because they're always in contact with the board itself. But yes, wedge gates would be one that you just really have to pay attention to.
Thank you, Richard. The next question, do you use gaskets inside the valve body? If yes, and what type?
So it depends on the size, and it also depends on the pressure class. But for most applications where we have extremely high pressures, a metal body seal is typically the way to go. Now, sometimes a gasket could be used if there's just not enough space for both of them. But those gaskets, and I'm really talking about general applications as distinct to hydrogen, and those pressure applications tend to be lower. So talking about class 300 or class 600, where a gasket would suffice. But for high pressure stuff, a metal body seal is really the way to go.
Thank you, Richard. The next question, if we can't use 316 stainless steel due to sulfide stress cracking, typically would we go for Inconel 625, but Inconel, as mentioned before, is subject to embrittlement. What possible materials are acceptable?
Yeah, that's a good question because it's always a subject of debate. So Inconel 625 is an excellent material when it comes to corrosion resistance. For any sour gas application, it's pretty much the go-to. It's a very good material. Of course, the downside is the effects of embrittlement. So I think there's not enough information out there as to which way to go. And I'm really talking about field experience because, do you go with Inconel 625 and then suffer embrittlement, knowing full well that you've solved one problem, which is the corrosion aspect? or do you look at another material, solve the embrittlement problem, but then the valve or the equipment could fail simply because of the corrosion? It's a good question. Internally at ValvTechnologies with our metallurgists, it still is the subject of debate because there's just not enough empirical information out there to say one way or the other.
Well, thank you, Richard. If there's any other questions, I encourage folks to just continue to put them through the chat. We're going to continue to stay online here for a few more minutes if there are questions. Richard, thank you very much. Great presentation, great understanding of the topic, and I think from what I've taken away today is really it's not a black and white scenario when it comes to working with hydrogen. We really need to dive down and understand the process, understand the application, and what type of hydrogen we're trying to work with and what the valve's jobs. So for any of those folks that are still on the call, if you'd like to speak more on this topic, CGIS, we'd be happy to come and tailor a presentation specifically to your organization or a specific project you may be working on. And just reach out to Sam when he sends the email out to everybody with the recording, and we'd be happy to set that up and talk in further detail and share our learnings and so forth in the world of valves and hydrogen. Richard, if you have any other last words, I'll leave the floor to you, and please send your questions through, and we will see you guys all on the next one. Thank you.
Yeah, thanks everyone. Thank you for listening. Really appreciate your time. And as Jason says, we're both here. We'll be setting up some follow-ups, certificates of training if anybody needs it. But we're here to ask or to help with any other questions that you may have. You can always email us or call us.
Thank you, Richard. Have a wonderful day, everybody. Take care. Stay safe.